Oh, good morning, everybody. Once again, welcome to the next installment of Cosmic Coffee, coming to you from Lowell Observatory. I'm Jeff Hall, and I'm here once again with Lowell astronomer Brian Skiff. Brian was on the show about a month ago. If you're one of our regular viewers, you'll recall we were talking about how we determine the distance to various objects in the universe, as well as how we measure the brightness of different objects. That those might seem like pretty basic characteristics, but with the kinds of distances we deal with in astronomy, they can actually be very difficult to determine. So for today's show, we're going to pull distance back down to the area right around the sun and talk about what we call the solar neighborhood. Think of this as an area, maybe if you imagine a sphere, 25 parsecs or so, 10 to 25 parsecs, or in the 40 to 80 light year size range. We're going to take a look at what the space around the sun looks like, particularly in regard to the stellar content. What are the stars nearest the sun, their characteristics? And this will riff a little bit on some of the things we talked about last time. And in fact, we're going to start with that. So to get this launched, I'm going to share a screen here, and then I'm going to call up the chat on my end to make sure I can see any questions you might have. And we'll just step through both what the region around the sun looks like, what its stellar content is, and then we'll talk a little bit about some of the longstanding research that's been going on here on nearby and sun-like stars, which is something that Brian and I have been pretty closely connected with over the past decades at this point. So first of all, we're gonna start by doing a summary from one of the well-known programs, well-established programs in this area, and Brian will tell you a little bit about that. So let's talk about the general characteristics of stars in the solar neighborhood to start with.
Well, this is a maybe confusing plot of what the nearby stars actually are. And the main thing to get from this is from Todd Henry's program, who is at Georgia State University and had a long-running program observing both from the north and the south, and including having students come to Lowell Observatory to work, basically inventorying in a very complete manner the very nearest stars out to about 30 light years, 10 parsecs in this sample. And the main thing to notice is that all the stars are the faintest red dwarf stars, and in fact the number of naked eye stars, at least readily visible naked eye stars that are in this red dwarf cohort that you can actually see if you go out at night, is zero. What are called the M dwarf stars there are no naked eye stars amongst that group. So and it's not because they're far away, it is that they're in fact quite close, but very dim. And there are indeed a few stars like the sun right at one solar mass over sort of towards the lower left of the histogram, and a couple of other stars that are brighter and more luminous, I should say, and more massive. But almost all the stars, 90% of the stars, are very small dim stars that are only a fraction, 2/10 of a solar mass or less even. And we've started to discover planets, which Todd has put it in green over on the very right edge of the plot. And in fact, this plot is now a decade old, and so there's more of those, but not a great many more of the planets. They're even dimmer and even harder to find.
Right, and we talked about that preponderance of low mass stars in the show about a month ago, and that the x-axis on this graph is that M over M sun. So that's basically the ratio of the star's mass to that of the sun. And these red dwarfs are not just barely not visible, they're really faint. So we're talking 10th, 11th, 12th magnitude at this point. So we do have a question in the chat, actually a very good question from Chris Georgie. Are other members of the solar neighborhood traversing the galactic disk in a path similar to the sun, or do they have high proper motion with respect to the sun?
So the answer is yes, both. The great majority of the stars are more or less in the plane of the Milky Way and in the disk of the galaxy, but there are a few stars that have high velocity. So a long time ago, from the 50s up through the 70s, Lowell ran a proper motion survey to look for stars that had large motion relative to background stars. This was done using photographic plates from the Pluto camera, in fact. And one of the results from that was to actually pin down much better the fraction of the stars that had large motion simply because they were near to us, and another fraction that were somewhat farther away but simply moving really fast compared to the sun going around the Milky Way and its general cohort. So there is a relatively small fraction that have these high motion, high space motion actually compared to the sun. And those are thought to be older stars, that some of which were actually cannibalized by the galaxy from accreting dwarf galaxies in the early history of the galaxy, as well as ones that had their orbits around the galaxy pumped up by interactions.
Right. And so we can see in the solar neighborhood, this one right over here on the axis. So that is one solar mass. That's the mass of the sun. And that's fairly far over in the distribution. So the sun is a pretty big fish, as it were, in the solar neighborhood. But if we turn things around, even if you're out at just 10 parsecs and looking back at the sun, it would be barely visible. It'd be about fifth magnitude. So even the sun, in the grand scheme of things, isn't that luminous a star. And we can see this graphically on the next plot, also from Todd's program. We can point out some of the labels. I know they're a little hard to read, but this shows the 25 star systems nearest to the sun. And there's some old favorites of ours in here, Ryan.
Yeah, there's the thing that's right in the center, the powder. Well, the sun is there just to the left of center, and it's kind of a middling sized dot amongst the dots. And then over to the right of it, the pale green dot ball is Sirius, which is by far the most luminous star amongst the very nearest stars. It's roughly 2 times the mass of the sun and about twice the temperature of the sun too. And Jeff just mentioned that amongst stars that the sun is kind of middling, and over on the right edge there's Tau Ceti, a bit down below, and that's a 4th magnitude star in the sky, and it's a little bit dimmer than the sun intrinsically, but it's the brightest star that you can see that's like the sun in the sky. And if you go out on an autumn evening and look up in Cetus and you see where its Tau Ceti is, it kind of puts you in your place that even amongst the very nearest stars, that a star like the sun itself is really not very luminous at all. And other features in this plot include Alpha Centauri, which is down below and to the left of the sun, which includes, it is itself a wide binary star. And in fact, there's a third component, Proxima Centauri, that's very slightly in the foreground compared to those guys, that belongs to that system. So it's actually a triple. And in fact, many of the systems, roughly half of the systems that are very near to us, are binary or triple higher order multiple stars.
Right, you can see that depicted here. There are just visually, there are a number here that are well-known pairs, like right up here, 61 Cygni A and B, and that's a group that we've long studied, and we'll get to that a little later in the show. And then, of course, right up here is Procyon. And if you go back to our show on the winter hexagon from 2 months ago at this point, we talk about both Sirius and Procyon. Those are 2 of the very bright stars in the winter hexagon here in the northern hemisphere. And it's only because they're so close. Even they are not all that luminous.
And indeed, they are both binary stars. You can see next to both the Procyon dot, or the ball, and the Sirius mark are tiny, tiny little dots. And those are both white dwarf stars that have started out much more massive than either of those stars, but have evolved already rather rapidly to become white dwarfs. And they are literally 10,000 times dimmer than either Sirius or Procyon, and very difficult to see in a telescope. And so there are burned out cinders of stars around these nearby stars, as well as systems that have comparable sizes and brightnesses.
Yeah, and of course, even here in our neighborhood, we can also now be talking about planets because probably everybody's heard about Proxima b. Right up here is Epsilon Eridani, another nearby star known to have at least one planet.
Right. And these are getting found rather gradually. And people looking out a little farther than this plot goes to find the planets, and they're right at the hairy edge technologically of what we can actually detect. And so an even more a stronger challenge is to find, or I should say, once we find them, to be able to actually find out something about those planets. So in fact, Barnard's star over here to the left of the sun, the small, very low mass star, only about 2/10 the mass of the sun, has, yes, that's right there, has a planet around it that's been found from the change in the velocity of that star. And that is indeed, Chris Georgi was asking about stars that have high speed relative to the sun. And Barnard's star is one of those halo stars from out in the halo of the galaxy that happens to be whizzing through this neighborhood just now. It's going about 100 kilometers per second compared to the motion of the sun. So it is an old high velocity star, but it also has a planet around it.
Yep. Very high proper motion star. And just in photographs from different epochs, you can see the thing cruising along relative to the background stars. Chris was also wondering what we know about the velocities of these stars and how they relate to the overall population of the Milky Way, presume, overall dynamics in the galaxy.
Yeah, we've been learning in the last 20 years particularly, and even more so just in the last 5 years from the Gaia spacecraft, which is providing these billions literally of motions and velocities for stars, that it's, well, the old idea that there was this spiral galaxy that's as flat as a pancake with this very diffuse halo of older stars around it is too simple, as a lot of things are in science. What we start out with are simple ideas, and turns out the world is more complicated. And what we've learned in the last 20 years particularly is that there are these huge streams of stars that have a coherent motion and around the galaxy that basically the idea is that they are dwarf galaxies that the Milky Way cannibalized throughout its history. And so that there are these streams of stars that have similar ages and composition and the velocities and motion around the galaxy. And that's a whole area of research that people have gotten into as a result of having these big surveys available that just didn't exist before. We just didn't have the data.
Right. Turns out cannibalism is actually pretty much a thing when you come to studying galaxies and how large galaxies were built from the carcasses of little ones, and still going on here in the local group. And if you have the right really sensitive technology, you can see these faint streams of remnant stars and gas from some of these little former dwarfs the Milky Way has eaten. So talking about surveys and acquiring data, we can talk a little bit, I think, about how we've approached studying some of these various stars right here, because this has been a topic of research at Lowell for the better part of a century at this point. I mean, really going on 70 years. And here's some of the instruments that I think we're both quite familiar with. Brian more so with the one at upper left than I.
I guess that's my cue to talk about our venerable 21-inch reflector here that was actually built in the early 50s for Harold Johnson. And he was an astronomer who was here for several years and invented the now standard UBV photometric system. And the standard stars for that system were done on this telescope in the 50s. And I spent about 1,200 nights running this telescope from the mid 80s up to about 2000, running this telescope with the photometer that's on the back end of the business end of the telescope. It's quite a complicated piece of work. But basically we ran a program for about 15 years to measure the brightnesses of a bunch of these stars that you saw in that previous diagram, looking for long-term variations related to the magnetic cycles on the stars, basically the sunspot cycles, like we see the 11-year sunspot cycle that we see on the sun. And that program ran for about 15 years, and we got a huge amount of data out from that, and basically learned that amongst stars, that the sun, amongst its cohort, was more boring than the neighboring stars in general, at least to the limit that we could detect. And so that perhaps one reason that we have been able to evolve here on the planet is because there haven't been huge magnetic storms or solar flares coming from the sun that have done bad things to biology on the planet.
Right, relative to many of the stellar cousins, and we'll have some plots in a couple of slides that show some of the fruits of your 1,200 nights at this ancient telescope, completely open to the sky. I admire you doing this all through the winter.
Yeah, this was old-fashioned kind of observing, where you're standing out at the business end of the telescope, running a computer and moving the telescope from star to star.
Yeah, and in contrast, this other facility, which is our spectroscopic facility, a program that we just brought to a close at the end of 2020, this is inside the dome of the 1-meter telescope. So this is a spectrograph that lets us observe the activity of the stars, which is a complementary data point to the brightness. And what we've been trying to do is compare how the brightness variations correlate with the activity for stars, as well as the sun. This right here is our little solar telescope. So it's just a fiber optic that tracks the sun. Sunlight comes through an optical fiber and eventually into this old spectrograph, which was built in the late 1980s. And we ran it through its paces for about 30 years, collecting these activity cycle data.
So the star list that we ended up observing with the spectrograph was almost the same list of stars that we observed photometrically with the old 21-inch telescope. And so those of us who were doing the observing from a comfortable control room in this case were familiar with the star designations, the HD numbers of the stars, and just the same old stars, looking at them continuously. And in this case, looking particularly in the violet part of the spectrum of the star, looking at spectral features, which we'll show you here, that are related directly to the spottedness of the stars, the sunspots on the stars, or star spots. and they're coming and going and increase and decrease depending on how they were, both at their activity level, both the rotation that we would see as the spots would come and go, but more interestingly for us was the long-term variation over many, many years, decades kind of timescales. And this is Jeff's cue to describe the spectra at this point.
Sure. I can take this slide. Yeah, so this is just a representation of what we see or might see if we could see some of these stars directly. So for reference, this here is the sun viewed in hydrogen alpha light, and you can see the dark spots there, and then the bright regions we call faculae around the spots. And then right over here, another star we saw in the diagram earlier. This is 61 Cygni A. I've used an image of the sun here, but I've scaled it down to about the size of 61 Cygni A. And then this up here is one of the most massive stars that we had in our program for a while, actually almost more of a reference star. This is Altair, prominent bright star in the summer. And then right here, you see the three grayscale spectra from our spectrograph of these three stars, of Altair, of the sun, and 61 Cygni A. And those ultraviolet calcium features Brian was talking about are right here. And you can see every spectrum is unique. This is like the star's fingerprint, basically.
So Altair is a relatively hot star compared to most of the solar neighborhood. And these big, broad, dark bands are actually just from absorption by hydrogen, the main constituent of the stars. And all the little fine lines all through here are from metals, titanium, iron, cobalt, magnesium, manganese. All those lines show up as very fine absorption features in the spectra. Then the middle one looks like a solar spectrum, And the Balmer lines from the hydrogen have greatly weakened, and the two big broad bands that you see near the middle are from this calcium, ionized calcium in the spectrum. And finally, at the bottom, the 61 Cygni spectrum is just blanketed almost entirely with these metal lines from the, if you remember your high school periodic table, that middle line of the spectrum of the periodic table, all those metals are showing up as those many, just literally millions of absorption lines in the spectrum, as well as very broadly, you see the H and K from calcium, very broad lines.
Right. And the calcium lines are the ones we particularly focused on because they are very sensitive to the presence of spots and faculae and plage in the star. In general, as we move to progressively cooler stars, so these spectra are arranged in order of decreasing temperature, you can see the spectrum becoming more blanketed, more complex, just because in the cooler stars, the physical conditions in the atmosphere allow the existence of atoms in the states that generate a lot of these lines. There's a good question from Chris that could take a fairly extended answer. I think he wanted to know, were any of the magnetic data correlated between stars proximate to each other or in relation to position in the galactic disk? And we could write a short book on all of that.
In fact, books have been written.
Yes.
But basically, that activity, well, in the case of the stars that are quite close to each other, that would be actually close enough to orbit each other, there is some effect where the stars really are, as close as we have the sun and 61 Cygni, those stars that are that close together actually orbiting each other, where the magnetic field and the activity, just surface activity of the star these two stars would be influencing each other. But in general, the activity level is related most strongly to the age of the stars, so that the young stars are very active and have these very strong magnetic fields, at least at the surface, that are broadcasting information about themselves. And as the stars, sort of like humans, as the stars get older, they get more boring. And so that in the case of the sun, it's relatively inactive. And in fact, there are stars that are older than the sun that we know of, and we're part of the program, that were actually more boring than the sun in terms of this measurement of the magnetic activity.
Right. We'll show you a couple in the final few slides here. But yeah, the activity here is a magnetic phenomenon. It's driven strongly, like you say, by age, which is correlated with rotation. And it's really the vigorousness of the rotation and the convective churn beneath the star's surface that's leading to the magnetic dynamo. And one thing we're starting to find out, the sun goes through periods where the activity cycle, or at least the large-scale manifestations of the cycle, turn off for 70 years or 30 years or several cycles. So the so-called Maunder minimum of the early 1700s is a good example. And that this may be an indication of a star that's beginning this transition sort of from its hedonistic youth to its boring old age, as it spins down and it becomes harder and harder for it to sustain that dynamo that keeps all of these interesting active features going. So we can show you a couple of examples of what stars in our solar neighborhood do. And Brian was talking about HD. It's pathetic how many of these random 5 and 6 digit numbers we just had memorized. It's like, oh yeah, 30495, of course. So here's a couple of classic examples of the kinds of activity, brightness, behavior that we see.
So at the top is everyone's favorite solar twin, star in Scorpius, in the very upper part of Scorpius. It has just a number, a running number, 18 SCO, and 18 Scorpii, and it is a star that has an activity that seems to have almost identical characteristics, even at very high spectral resolution in terms of the chemical composition, the age, the rotation speed, all very similar to the sun. And it's a faint naked eye star. And the activity level you can see, nevertheless, we were able to measure in the top plot of the two plots for that star. And is just showing a relative activity based on the strength of the amount of activity change basically in these calcium emission features that are associated with sunspots or star spots on the star. And then a colleague, not Todd Henry, but Greg Henry in Tennessee, has been running automatic telescopes that basically followed on from what I was doing manually at the 21-inch here on Mars Hill, but they applied some simple machine automaticness to get very high precision photometry, just measuring the brightness of the stars for a huge collection of stars and a huge collection of data. And you can see that in this plot, the second plot is showing the change in the brightness. It's actually in magnitudes, but it's in three. You can see it's only 1,000th of a magnitude half amplitude, so only 2/10ths of a percent change in brightness. So it's a very tiny variation, actually very slightly larger than the sun, but not very much different than the sun. But you see that the variations are roughly correlated in brightness with the change in this activity in the upper plot, so that they go so this, when the star is more active, the star, even though there's more star spots, the star is actually very, very slightly brighter than it is when there's no spots, which is an interesting effect having to do with the bright plage or the rice grains you would see when you look at a through a telescope at the sun visually with the right kind of filter.
Right, which is what the sun does. So the sun's brightness also varies directly with its activity. So at the peak of the solar activity cycle, the entire sun is about 0.1% brighter than at minimum. And that has caused a lot of interest in both the astronomical as well as the terrestrial community in sort of understanding the degree to which that fluctuating radiation impacts decadal scale and longer changes in climate.
Yeah, so interestingly, the sun and 18 SCO seem to be in this mode where the stars are actually, both stars are actually a little bit brighter when there's more spots. That seems to be compensated for by the bright plage around the sunspots. And but in the case of HD 30495, it's a younger, more active star, and we see and you can see by this S value that it's almost double the sun's activity level, even though the stars are almost the same temperature, and that in this case the brightness is anti-correlated with the activity level. So when there's more spottedness, the star is actually dimmer. And we think in this case that the stars are active enough that the spottedness actually it dominates the variation in the brightness, so that the star sure enough gets dimmer when it's more active. Right. And it's also spinning around faster. The rotation period is only a few days compared to almost a month for the sun.
Right, and you can see the impact of that and just how variable this star is. If you look at the y-axis here versus the y-axis here, there's a missing zero. So this is 10 times the variation.
Yeah, that's one that can actually, it's actually relatively easy to measure photometrically. Measuring the brightness change in the star is easy to do, where it's right at the technological limit, at least from the ground, to measure 18 Scorpii.
Right, and if you look carefully, it's active enough. If you look at these 3 points right here, those 3 there, then these, this, the anti-correlation is just beautiful. I mean, it's not approximate. It tracks, year to year very precisely. And Brian was mentioning this S. This is sort of just a dimensionless index that we use to characterize how much emission there is in the spectroscopic calcium lines. And the sun, for reference, this horizontal line right there is about, it's the median of this data series, but it's very similar to the sun, which is about 0.17, whereas down here 0.3 is a really, really active star. Question, is the brightening homogeneous across latitude or localized near the equator? Yeah.
That's a great question. And people, again, have because of the magnetic fields, people have done a tremendous amount of modeling for that and trying to identify it on, actually resolve individual features on stars at high resolution, either spectroscopically or actually doing it with other instruments. And the answer is is that there's quite a bit of variation. So in the case of the sun, at the start of the sunspot cycle, the 11-year sunspot cycle, the spottedness is at relatively high latitudes away from the equator of the rotation of the star, and it trends downward toward the equator by the end of this 11-year cycle. But for really active stars, when people do the modeling, often they end up with a spot right at the poles, and I don't understand the magnetohydrodynamics well enough to tell you why that should happen. But if the star is spinning rapidly, and then there's this spinning magnetic field that's inside the star that gets coiled up, you can have the thing end up at the poles. And often we see that in the case of binary systems, where we know what the orientation of the system is, in terms of where the rotation axis of the orbit of the companion star is, so that we think we know where the stars are pointing, where the poles are pointing. And it often ends up that for the active stars, that the spots end up at the poles a lot. But it's not necessarily well defined, because we can't see, we haven't been able to send the CubeSats out to actually go to a star and sit there and say, here's what happens.
It's a really difficult calculation. First of all, we should say for these young stars, these spots are also, don't picture the nice little roundish spots we have on the sun. These are like these giant birthmarks almost that are splattered across a large fraction of the star's surface. If you looked at the sun, I would say, the so-called butterfly diagram is fairly symmetric. You see a fair amount of activity in both hemispheres. Another reason it's very difficult to try and do any kind of localization of where the activity is just from the spectra, though people have tried to do it and have tried to measure differential rotation just from the spectra, and that's really, really hard to do.
Yeah, so I was saying spots and spottedness, but you might think of them as active regions rather than just a single classical sunspot.
Right. So to show you a little bit of the kind of zoo we have here in just within our own sample and in the solar neighborhood, we'll our last slide this morning just shows you a sample of the different kinds of variability that we see, even from stars very much like the sun. And here's 18 Scorpii for reference again up here. These are our spectroscopic observations. And then, you see stars that are just very different.
So often for the young stars, it seems that if there is a cyclic variation, the cycles are quite short. And as you can see in the bottom two panels here, for these two fairly active stars, that it's almost as though there's one year's up and 1 year's down. And it's probably just that the variation is just jittery from year to year or from season to season, and that if there is a cycle, that it's not expressing itself very well. And Jeff has put in these plots, rough periods for 13974 of 6.5 and 2.5 years, and for HD 22049 about 3 years. So it's a little bit longer than you can just resolve it on a seasonal time scale. Whereas for 18 SCO in the upper left, it's about 6.5 years if we believe our cycle of data. And if we had 500 years rather than 20 or 30 years of data, we might change our minds. But a lot of stars, one of the questions we've had here is whether the sun's 11-year cycle is unique to the sun. And indeed, one of the questions we had when we started the photometry program back in the 80s was, are the cycles shorter? Are they longer? Or could they be, many lifetimes, human lifetimes, 50 years or hundreds of years? And we didn't know back in the 80s. And now we've collected enough data that we see that there's quite a variety, and that the relationship is complex. It's not a simple, age kind of thing necessarily.
No, it's not. And, I was going to say we could observe for 500 years, but I would be completely sick of this project by then. I will.
We might actually know the answer.
We might actually know the answer. But there are a lot of interesting things in here. Brian mentioned the cycle periods, and here we actually think we see two. And we get those by taking these data series, and we essentially run them through something akin to a Fourier transform to extract the time scale of periodic signals. And in this case, 22049 this is actually Epsilon Eridani.
Epsilon Eridani, yeah.
Yeah, right. And first of all, it's this very fast 3-year cycle. Interestingly, the program that preceded ours at Mount Wilson back in the 1980s saw no cycle at all. The star was just jittering very irregularly, and then suddenly it settled into this rigorous 3-year cycle. So this is an example of seeing stars changing their behavior just on the time scale of our program. We also mentioned this is a system that has a planet, and look at the S value here, 0.5. I mean, this star is crazy. And this is an example of where a planet might be rendered inhospitable just because the star is going bonkers.
Yeah, unless you have a really robust ozone layer to protect you from the ultraviolet energy coming in, you might, or down at the bottom of some ocean around this, on the planet around the star, have to have a pretty tough shell to survive. And there, as someone joked at a conference about these young stars, there's be a lot of static on the radio if you lived here.
Yes, exactly. Yes, a couple of comments in the chat. Chris says he'd love to learn more about stellar magnetohydrodynamics. I think the astronomical community would as well. I mean, this is how you understand and model the origin and nature of stellar activity cycles, but it's a ferociously difficult problem and very computationally intense when you try to do it in 3 dimensions. So there's a lot about the nature of stellar dynamos that we don't really understand very well.
Yeah, the word magnetohydrodynamics is a big, long word because it's a really complicated subject.
Right, the longer the word, the more difficult the math. Another very appropriate comment from David Connell is just to remind all our viewers that our very own Brian Skiff here is, quote, considered one of the most respected, prolific, and important observers of our time, which I certainly concur with. I feel like Brian's forgotten a lot about this topic, more than I'm ever going to know, probably. So we're very fortunate to have you on the staff.
It's just a lot of nights at telescopes, a life in the dark.
Right. So we'll ask for any further questions on the chat feed from our viewers. I would like to note, Brian referenced something right towards the end of today's show that's going to tie perfectly to next week. And that was, to the question about how are active features distributed on stars, it's really hard to tell because they're so far away and we just see them as point sources. But with the right kind of instrumentation, you can actually try to do that and make images of stellar surfaces. And next week, I'm going to be here with our astronomer, Gerard Van Bell, who's one of the world experts in interferometry. And we're going to talk all about interferometers. This is sort of the cosmic coffee thread on astronomical instrumentation and tools that we do kind of mid-month. And we operate an interferometer right here at Lowell. There are several others around the world, and these are instruments that let you try to do that kind of work. So join us next week for Cosmic Coffee to hear all about interferometers. Thanks as always for watching. Thanks to Brian for joining me to talk about the really interesting beasts just within 10 or 20 light years of the stars. Oh, one question did come in from Chris, and this is another good one. How much mass outflow do we get from the active areas on these young stars? Good question.
Need to get Lisa Prato and our grad student Lauren Biddle on to talk about this stuff on the very young stars. So it's a modest amount of mass. It turns out the star doesn't shrink down to nothing. It takes a long time for that to happen. So it's millionths of a solar mass per year kind of range, even tens tenths of a millionth of a mass, solar mass. And so it's, even though the activity is very bright and very prominent, it's mostly because that tenuous gas gets very hot that we can see it, and it seems like there's a lot of activity, but the amount of stuff involved compared to the mass of the star itself is actually quite small.
Right. And really, we would at some point get our astronomer Phil Massey on here as well, because he studies the kinds of stars that do have these incredibly strong winds, and the outflow from the wind is strong enough to be a significant impact on the overall evolution of the star, because it really is a millionth of a mass per year or something, which on a stellar lifetime, that can really start to add up.
It only means it only lasts 1 million years, unless something changes. So yes, small amounts, usually.
What kind of ratio compared with the sun's mass outflow? Well, we're talking several powers of 10. I mean, the most massive stars have, winds that they're losing mass at what, 10,000, 100,000 times the rate. I'd have to look it up, but it's several orders of magnitude. So with that, we'd like to say thanks for watching. Thanks again to Brian, and join us again next Thursday to talk about the weird, wacky world of interferometry. Should be a fun talk. Gerard's very good at explaining the arcana that go into doing that. So until then, stay well, stay safe, and we'll see you next time.